Hello, and welcome back to this course, Logic, Circuits, and Design. In the previous video, we talked about the introduction to the course Digital Logic, Circuits, and Design. In this video, we will talk about what number systems are and the most common number systems that we will use in the Logic, Circuits, and Design course. If you want to follow along this course, please do hit the like and subscribe button, as that will inspire me to create more videos like this. Now, let's get started. Number systems are different representations of numeric data. The most common number systems are the decimal number system, which is a base 10 or radix of 10, binary, which is a base 2 or radix of 2, octal, base 8, and hexadecimal, base 16. But before anything else, let's try to understand the differences between bits, bytes, and nibbles. If you haven't heard of this before, well, let me introduce you the binary numbers system. Binary numbers are what we usually use in digital logic, circuits, and design. It represents two levels of status in electronics. Zeros represents off and 1 represents on. Now, a bit is a digit or a single digit of the binary system represented by zeros and ones. So each of this here is called a bit. So how many bits can you see here? We have 8 bits, correct. Now, what about bytes? A byte is a unit that represents with 8 bits. So a group of 8 bits is called a byte. This here is 1 byte. A nibble is a unit that represents with 4 bits. So a group of 4 bits is called a nibble. Now let's continue with decimal numbers. Decimal numbers are base 10 numbers that we often use in our daily lives. Let's take, for example, this number 846. Back in our elementary years, we learned about place values. The ones place carries a value of 10 raised to the power of 0, which is equivalent to 1. The tens place represents a value of 10 raised to the power of 1, which is equals to 10. And the hundreds place carries a value of 10 to the power of 2, which is equals to 100. 6 here is the least significant bit, as it carries the least place value. And the 8 here is the most significant bit, as it carries the highest place value. A binary number is a number expressed in the base 2 numeral system, represented by zeros and ones. Since this is a base 2 number system, our place values would be 2 raised to the power of 0, 2 raised to the power of 1, 2 raised to the power of 2, 2 raised to the power of 3, 2 raised to the power of 4, and 2 raised to the power of 5. The number here at the bottom are just the equivalents of this one. Now, how do we represent this number 52 into binary? To get the number 52, let's just add the place values, which carries the digit 1. So let's try. 32 plus 16 plus 4 is equals to the decimal number 52. Now there's another way to convert a decimal number to a binary number. This one is called the continuous division. Let's take, for example, the number 25. We need to divide it with 2 until we get 0. Let's start. 25 divided by 2 is 12 plus a remainder of 1. 12 divided by 2 is 6 with a remainder of 0. 6 divided by 2 is 3 with a remainder of 0. 3 divided by 2 is 1 with a remainder of 1. 1 divided by 2 is 0 with a remainder of 1. In order to write this one, this is a from top to bottom approach. So this number on the top is the least significant bit, and the number at the bottom is the most significant bit. So if we write it down, we start with 1, 0, 0, 1, and 1. Let's take another example. 3. 3 divided by 2 is 1 with a remainder of 1. 1 divided by 2 is 0 with a remainder of 1. So this is how we represent the number 3. Now we have hexadecimal numbers. Hexadecimal numbers are based on a radix of 16, meaning this system uses 16 digits as representation. To represent the numbers, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And to represent the number 10, 11, 12, 13, 14, and 15, we have A, B, C, D, E, F. F here is the last number, which is 15. We usually use binary numbers as a representation. However, when binary numbers gets way too many, it's hard for us to read, which makes it prone to errors. To simplify this, we instead use hexadecimal numbers. So, when we turn our binary number into a hexadecimal number, what we do is we divide it in terms of 4, or we divide it into nibbles. Remember what nibbles are? This is how they look like. So why do we use 4, or why do we divide it into nibbles? It's because 2 raised to the power of 4 is equals to 16. And since hexadecimal numbers has 16-digit representations, so each of these groups of 4 have 16 number representations in them, ranging from 0 to F. Now let's check. In this group, we have 8 plus 4 plus 2 plus 1, which is 15, equivalent to the letter F. Now let's try to check the hexadecimal representation for this binary number. Let's start with the first nibble. 4 plus 2, 6. 8 plus 4 plus 1, 13, which is letter D. 8 plus 2 is 10, represented by letter A. 4 plus 2, 6. 4 plus 1, 5. 8 plus 2 plus 1, 11, represented by B. 8 plus 2, 10, represented by A. 8 plus 4 plus 2 is 14, represented by letter E. Now if we program in C, assembly, and Java, it's common to see the symbol 0x before your hexadecimal number. Now how do we convert decimal to hex? Let's try the decimal number 230. First, we represent this number into its binary equivalent. We have 111001110. Let's check. 128 plus 64 plus 32 plus 4 plus 2. It's 230. Now that we have our binary representation, the second step is we represent them into nibbles, or by 4 bits. We have here 4 plus 2, 6. 8 plus 4 plus 2, 14. So the hexadecimal equivalent is E6, or in assembly programming, it's 0x E6. How do we convert it back to decimal? First, for each of the characters, we represent them with 4-bit binary numbers, or nibbles, right? So for 6, we have 0110, and for E, we have 1110. Now that we have our binary numbers back, then we will combine these 4-bit groups in one long binary and add them using the binary place values. So the original place values for binary is 1, 2, 4, 8, 16, 32, 64, 128. Let's just add the place value and we will get back to our decimal number. 128 plus 64 plus 32 plus 4 plus 2 equals 230. To sum up, this table here shows the comparison between decimal, binary, and hexadecimal number systems. Wow, you have such a great passion. You have followed this video all the way up here. Keep it up. And if you find this helpful, please consider hitting the like and subscribe button as it inspires me to create more videos like this. Up next, we will talk about the operations on binary numbers. Stay tuned.